Welcome to part 1 of a video tutorial series on organic functional group reactions. This tutorial will focus on introducing the reactions that will be covered in the series and a brief review of acid-base chemistry. Let's get started. So it's really important to note that each functional group has unique chemical reactivity, and so this section is going to set us up for biochemistry. Biological molecules can be very large, so we have to remember to focus on the functional group. The bulk of the molecule will simply symbolize as R for rest of the molecule. And we will be focusing on a very small aspect of the molecule, but that's where the chemical change is occurring. So most reactions only affect one functional group at a time. So recognizing the functional groups and looking for changes is a really great strategy to help make sense out of this. So let's practice that skill first. Look at our reactant and product and then go ahead and circle the change that you see occurring. So notice we have two functional groups, right? But that the carboxylic acid remains the same. We can see that the ketone is changing into an alcohol. So that's where we would focus our attention then on, and this is what we're going to learn, what type of change that is. So we'll get to that. But right now, we're just training our eye to look for changes. Now, it's important to connect all of this to what we've been learning about reactions. And so all biochemical reactions are pretty much catalyzed by enzymes, especially the ones involving functional group changes. So functional group reactivity. Alrighty, so catalysts. Let's remember, what are catalysts, right? They're a substance that decreases the activation energy to increase the reaction rate. And the interesting thing about a catalyst is that it is not consumed in the reaction. So the great thing about a catalyst is that we only need a small amount and it can be reused over and over. It catalyzes a reaction and then it's ready for the next set of reactants. Enzymes are especially important in our bodies. If we're in the lab, we can boil it or put some strong acid or base or some kind of heavy toxic metal, and in the reaction flask it's fine. But inside our bodies, right, we need to be gentle. We want to have our pH at approximately 7.4. We want to be at body temperature, right? That sort of thing, to keep our cells alive. So we can't use extreme reaction conditions. We need to benefit from the catalysts, which are enzymes. So let's kind of do a brief recap of what we know about reactions and how we describe them using a diagram. So we'll do a one-step exothermic. So as soon as you hear the word exothermic, you think negative X, heat as a product. And then in this case, we're going for a large activation energy. So that's a large E sub A. And so if we write our diagram, make sure I can fit it in the space. Okay. So of course it's time on the X, energy on the Y. So this reaction, right, large activation energy, products are more stable than reactants. So there's our reactants and our products. And so this exothermic part is here. And then the large activation energy is here, right? And the top of the curve here is our transition state. Okay, so now let's overlay a second curve. We'll use a dashed line for the catalyst. So what the enzymes or the catalysts do, we remember, is they lower that activation energy. So now we have a much smaller activation energy. And so this reaction can happen much faster because we have a much smaller hill to climb. If you had to run to the top of this hill, you could do it much faster than you could run to the top of this big hill. Alrighty, so we want to be keeping all of these concepts in mind as we think about the reactions. So we'll go to the next page and let's do a brief review of acid-base reactions, because these are the most frequent and fundamental. So they are always occurring in the background. So let's focus on some acid-base chemistry. So here we have an example of pyruvic acid, and this is a compound that we'll see when we learn about glycolysis and other biochemical reactions. And we recognize that it's the acid. And then of course we always see sodium hydroxide as a base. And so we know that the acid is the proton donor. So the pyruvic acid will donate its proton, right? And so noticing that the reaction is only happening at one functional group. So it'll give its proton to the hydroxide to form water. And then we have this sodium. It's basically a spectator ion. And so it'll be floating around as a counter ion to our pyruvate. And if we look at this, this complex here, right, we would describe this as a carboxylate salt. Okay. Now, let's look at another reaction. So here we look and there's two phenols and an alcohol and amine. And we look and we see an acid. So we recognize amines as weak. This is the weak base part. We have a weak base. And you've memorized your strong acids. So you look here at hydrochloric acid and you recognize it as an acid. So the base is the proton acceptor, right? Hydrochloric acid will protonate the amine. So notice that, the bulk of the molecule, right? Nothing's changing. We could basically think of this as a giant R group. And that's where we're headed. All right, and then we have the methyl group coming off, and then we would have H2 plus and the chloride. And so we would have created an ammonium salt. Okay, so then remember the importance of the ionized form of the carboxylate and the ammonium salt, right? That creates water solubility. So if we look at this, this next set of exercises, it's a good opportunity to practice classifying your functional groups and then predicting water solubility of the reactants and the products below. So we can see here with this large hydrocarbon group, we describe that as a fatty group. It's hydrophobic. And then we have our carboxylic acid group, so we would classify this as a fatty acid. And then there's our hydroxide. Here we have the carboxylate salt. Right? So the fatty acid is not water soluble. This large hydrocarbon region repels the water. So even though we have a polar group here that's weakly acidic, it's not strong enough to offset all of these nonpolar hydrocarbons. However, as soon as we have a full charge, now the carboxylate salt is water soluble. And another name for this carboxylate salt is soap. All right. And then we'll practice the other way. So here we have our amine. And we could be more specific. What type of amine is this? And we see there are two R groups coming off of the nitrogen. So the most accurate would be a secondary amine. And This one, there is some H bonding here, but there's also quite a few nonpolar groups. So this one we would expect to have very low water solubility because it's right at the cusp of that ratio, right? We know that the polar groups can solubilize, right, up to 4 to 6 nonpolar carbons. So this one's right on the cusp. So there's might be a little bit of water solubility, but very low. Not enough to really be useful if we want to have this in an aqueous solution. So we take our weak base, we react it with the strong acid, and we produce the ammonium salt again. And then that's the power of charge, right? With that full charge, then water soluble. Okay, so acid-base reactions are always possible. So they're going to be like a veil that's layered above, before and after any reaction that we perform. So we always want to keep acid-base chemistry in our awareness. So let's look a little more at the energetics though and tie this to what we talked about with enzymes and catalysts and things. So while I mentioned, right, pretty much the biochemical reactions where the functional group changes, they have the large activation energies. But we have to compare those to acid-base reactions which have a very low activation energy, small. All right, so when if we're looking at an acid-base reaction and we're doing a reaction energy diagram, so if we just simply think about, for example, HA, right, just a simple deprotonation, we'll just represent this as any weak acid. When we go to do the reaction energy diagram, it almost looks flat, right? We have a very small E sub A. It's so small I can't even really draw it in. So we're always, so if you're ever frustrated and saying, I wish there was a proton there, or I wish that proton would go away, you can always use whichever form makes the most sense to help you understand and predict the reaction. When we're doing our biochemical reactions though, at the very end we need to remember that physiological pH, right, is 7.4. So when we're all done, we will show all of our biochemical products at pH 7.4. So now let's look a little more closely at the implications of that large activation energy, right? So we know with a small E sub A, it's a fast reaction, right? But with a large E sub A, it's a slow reaction. So if we look at our reaction energy diagram, right now we're going to have a large activation energy. So if we just have two compounds coming together to make a product, this is going to be very slow. So that's why we need the catalyst. So the reactions that we're learning now, when we get to the protein chapter, we will learn about, right, with the catalyst, which we're learning in biochemistry would be the enzyme, right? We lower the activation energy and increase the reaction rate. So that's why enzymes are so important to our health. Now let's, as we transition to biochemical reactions, let's keep this all, keep focused on our target. So our target is to understand metabolism. So understand that metabolism is a combination of catabolism and anabolism. And to keep these straight, catabolism is the breaking down of molecules. And anabolism is the building. And so when I was like first learning this, I always thought about, you hear about the athletes, they use anabolic steroids, right? They use anabolic steroids because they're trying to build their muscles. So catabolism is about the breaking down. So as we learn these functional group reactions, keep in mind our end game is to get to understanding catabolism and anabolism. So when we think about food, we think about large molecules. And then catabolism is going to break them down. These will be some waste, like we exhale CO2 and release water. And then we get two very important things. We get energy and we get some small molecules. So we take the large molecules from our food and we break them down, and then we will rebuild them anabolically into the large biomolecules that we need to support our health. Alrighty, so there are many important biochemical reactions, and the four that we're going to study in this chapter in particular are oxidation and reduction. Alright, and because these always occur together, we can simplify the name to redox. A little easier to say than oxidation and reduction. And then we will focus, we're water-based. We have we're bags of salt water walking around. And so we will look at hydration, which will be the gain of water, and dehydration, the loss of water. And we will see here that it focuses on, this reaction will focus on functional group changes, primarily, mostly with the carbon-carbon double bond. And then we will look at the acyl group transfer reaction. And so here's an acyl group. We'll talk more about that when we get there. And the main thing, or maybe we'll use a question mark, right? So the acyl group is this part right here. So the acyl group is this part, and the reason why we call transfer is this question mark here, is this, we can vary, right? We can change what the acyl group is bonded to. So we'll explore that reaction. And then the last really important reaction that we're going to learn about in this series is the phosphoryl group transfer. So similar to the acyl group, but the phosphoryl group. And so of course that's going to have the phosphate in it. And we can go here. So there's phosphate, or we could put an R there, phosphoryl group. So those will be these will be the four reactions that we are going to learn about and study in the following video tutorials. So this would be a good time to take a few minutes to work through some introductory homework problems to reinforce your understanding.